NENOMATICA, where mathematics meets YouTube excellence. Welcome to our mathematics video. Today we'll explore an interesting algebraic identity involving three terms and their squares. This identity relates the sum of squares of three terms to the square of their sum minus twice their products. Let's start by stating the theorem. The theorem states that the sum of squares of three terms, a, b, and c is equal to the square of their sum minus twice the sum of their products. We can write this mathematically as a squared plus b squared plus c squared equals the quantity a plus b plus c, all squared, minus 2 times the quantity ab plus ac plus bc. This is a very useful algebraic identity that has applications in various mathematical problems. Before we dive into the proof, let's visualize what this identity means geometrically. Here we have three squares with sides of length a, b, and c. The sum of their areas represents the left side of our equation, a squared plus b squared plus c squared. Now, let's consider a larger square with side length a plus b plus c. Its area is the square of a plus b plus c, which appears on the right side of our equation. But we need to subtract something from this larger square to get our sum of individual squares. We need to subtract twice the sum of the rectangular areas formed by each pair of values, a and b, a and c, and b and c. This geometric interpretation helps us understand the identity intuitively. Now, let's move on to the proof of this identity. The proof is quite straightforward, but it involves careful algebraic manipulation. We'll start by expanding the square of the sum on the right side of the equation. The square of a plus b plus c equals a squared plus b squared plus c squared plus 2, ab plus 2, ac plus 2bc. This is just an application of the binomial theorem for expanding the square of a sum of three terms. Now, let's rearrange this equation to isolate a squared plus b squared plus c squared. We can subtract 2, a b plus 2, a c plus 2bc from both sides. This gives us a squared plus b squared plus c squared equals the square of a plus b plus c, minus 2 ab minus 2 ac minus 2bc. We can factor out the 2 from the subtracted terms to get a squared plus b squared plus c squared equals the square of a plus b plus c, minus 2 times the quantity ab plus ac plus bc. And this is exactly the identity we stated at the beginning. Let's verify this identity with a numerical example. Let's choose it equals 2, b equals 3, and c equals 4. For the left side of the equation, we compute a squared plus b squared plus c squared, which is 2 squared plus 3 squared plus 4 squared equals 4 plus 9 plus 16 equals 29 for the right side. We first calculate the square of a plus b plus c. The square of 2 plus 3 plus 4, which is the square of 9, equals 81. Then we calculate the square of 9 equals 81. Then we calculate twice the sum of their products. 2 times the quantity ab plus ac plus bc, which is 2 times the quantity 2 times 3, plus 2 times 4, plus 3 times 4 equals 2 times the quantity 6 plus 8 plus 12 equals 2 times 26 equals 52. So, the right side equals 81 minus 52, which is 29. Both the left and right sides equal 29, which verifies the identity for these values. Welcome to this mathematical video tutorial. Today, we'll be solving a problem involving a system of equations. We'll find the value of a product sum expression using algebraic identities. Let's start by looking at our example. We're given that a plus b plus c equals 10 and a squared plus b squared plus c squared equals 50. We need to find the value of the expression ab plus ac plus bc. We'll solve this problem using an algebraic identity. The identity states that a squared plus b squared plus c squared equals the square of a plus b plus c, minus 2 times the sum of products, ab plus ac plus bc. Let's write this more formally. Now, let's substitute our known values into this identity. We know that a plus b plus c equals 10, and a squared plus b squared plus c squared equals 50. So, we can substitute these values into our identity. We have 50 equals 10 squared minus 2 times the quantity ab plus ac plus bc. Notice we're using the fact that the square of 10 is 100. Let's simplify our work by denoting the sum of products as capital S. Let's define S to be equal to AB plus AC plus BC. This makes our equation 50 equals 100 minus 2 times S. Using substitution like this can often simplify complex algebraic expressions. Now, let's solve for S. we have 50 equals 100 minus 2s. Let's move terms around to isolate s. We get 2s equals 100 minus 50, which is 50. Dividing both sides by 2, we find that s equals 25. Thinking phase quick challenge. Verify this result by checking if it satisfies our original equation. Now that we've found the value of s, let's substitute it back to our original expression. Since s represents ab plus ac plus bc, and we found that s equals 25, we can conclude that ab plus ac plus bc equals 25. Therefore, the final answer is ab plus ac plus bc equals 25. Let's look at our example. We have two equations. First equation, a plus b equals c plus 6. Second equation, a times b minus a times c equals b times c minus 1. To solve this problem, we'll use an important identity from algebra. The sum of squares identity tells us that a squared plus b squared plus c squared equals the square of the sum of a, b, and c, minus twice the sum of their products. Now, let's start applying this identity to our problem. First, we need to find the value of a plus b plus c. From our first equation, we know that a plus b equals c plus 6. Let's rearrange this to find a plus b plus c. Now, let's square this expression. We have a plus b plus c equals 2c plus 6, so the square of a plus b plus c equals the square of 2c plus 6. This gives us 4c squared plus 24c plus 36. Next, we need to find the value of 2 times the sum of the products. We need to calculate 2 times the quantity a times b plus b times c plus a times c. From our second equation, we know that ab minus ac equals bc minus 1. Let's rearrange this equation to isolate the product terms. Adding ac to both sides, we get ab equals bc minus 1 plus ac, which simplifies to ab equals bc plus ac minus 1. Now, let's substitute this expression into our formula for 2 times the sum of products. We have 2 times ab plus bc plus ac. Substituting our expression for ab, we get 2 times the quantity bc plus ac minus 1 plus bc plus ac. Let's simplify this expression. We have 2 times the quantity 2bc plus 2ac minus 1. Distributing the 2, we get 4bc plus 4ac minus 2. Now, we have all the pieces we need. Recall our initial formula. A squared plus b squared plus c squared equals the square of a plus b plus c minus 2 times the sum of their products. We found that the square of a plus b plus c equals 4c squared plus 24c plus 36, and 2 times the sum of their products equals 4bc plus 4ac minus 2. Now, we need to substitute c plus 6 for a plus b from our first equation. We have a plus b equals c plus 6, which means a plus b minus c equals 6, or a plus b equals c plus 6. Let's continue our calculation. We're going to substitute c plus 6 for a plus b in our expression for 4bc plus 4ac. We can rewrite this as 4c times a plus b, which equals 4c times c plus 6, or 4c squared plus 24c. Now, let's go back to our expression for a squared plus b squared plus c squared. We have a squared plus b squared plus c squared equals 4c squared plus 24c plus 36 minus 4c squared minus 24c plus 2. Let's simplify this expression. The 4c squared terms cancel out, the 24c terms cancel out, and we're left with 36 minus negative 2, which equals 36 plus 2, which equals 38. Therefore, the value of a squared plus b squared plus c squared is 38. Let's look at our example. We need to find a complete expression for a squared plus b squared plus c squared, given that 1 over a plus 1 over b plus 1 over c equals 0. Let's start by working with the equation we're given. We need to manipulate the equation 1 over a plus 1 over b plus 1 over c equals 0. First, we'll apply a common technique for equations with fractions, multiplying all terms by a common denominator to eliminate the fractions. Now we'll use the trinomial square identity to help us find a squared plus b squared plus c squared. The trinomial square identity states that the square of a sum equals the sum of squares plus twice the sum of all possible products. That is, a plus b plus c. Squared equals a squared plus b squared plus c squared plus 2 times ab plus ac plus bc. From our previous step, we know that bc plus ac plus ab equals 0. Looking at the trinomial square identity, we can see that the term 2 times ab plus ac plus bc is equal to 2 times 0, which is 0. Therefore, the trinomial square identity simplifies to a plus b plus c squared equals a squared plus b squared plus c squared. Finally, we can rearrange the equation to express a squared plus b squared plus c squared in terms of a plus b plus c squared. So, a squared plus b squared plus c squared equals a plus b plus c squared. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.